Hello and welcome to the Algebra 2 Regents live review by eMath Instruction. My name is Kirk Weiler, and tonight we're going to be going through the June 2022 Algebra 2 exam from the first question to the last question to help you get prepared for your Algebra 2 exam. Your Algebra 2 exam will be on Wednesday this year, but please consult your local school district in terms of the time of the exam and, of course, how to get to the exam. Anyhow, I hope you have the exam printed out and kind of ready to go. So let's start going through the questions. And of course, we're going to start with our multiple choice. Let's get into it right now. All right, here we go. Let me just bring this up to the top. Now, the multiple choice section on the Algebra 2 exam constitutes 24 questions, right? Just like our other two Regents exams, those 24 questions are 2 points each with no partial credit. So you want to make sure to read the question carefully, try to select the best choice after you've worked through the problem, and then, of course, you'll want to bubble the right choice on your Scantron sheet. All right, let's get right into it with question number 1. For all positive values of x, which expression is equivalent to x to the 3/4? All right, now many of you will have already kind of seen this and said, okay, I know exactly what answer that is, all right? But here's kind of the way we want to think about it. And I just want to go over a real quick exponent property that's going to pop up repeatedly on this test, right? There's this exponent property, and let me turn this into blue. I just like blue better, where if I have x raised to the m raised to the n, that's x to the m times n. Now, that particular exponent property can actually move in both directions, and here's what I mean by that. I can rewrite x to the 3/4 as x to the 3rd raised to the 1/4. All right? So 3 times 1/4 is 3/4. So I can rewrite x to the 3/4 as x to the 3rd raised to the 1/4. And what I learned in Algebra 2 was that the 1/4 power is the same as the 4th root. And therefore, x to the 3/4 is the same as the 4th root of x cubed. And that's choice 1. A nice standard question. If you were paying attention during fractional exponents in Algebra 2, this one was probably a gimme. Let's take a look at question number 2. Mrs. Favada's, I'm probably not pronouncing that right, Mrs. Favada's statistics class wants to conduct a survey to see how students feel about changing the school mascot's name. Which plan is the best process for gathering an appropriate sample? All right, now I kind of wish they had, instead of used appropriate sample, used the word representative sample. In other words, right, we're not going to go out and do a census of all the students, right? We want to get a sample that represents a broad cross-section of the students. So let's take a look at the 4 choices. Choice 1, survey students in a random sample of senior homerooms. Choice 2, survey every 10th student entering art classes in the school. 3, survey every 4th student entering the cafeteria during each lunch period. And 4, survey all members of the school's varsity sports teams. All right, now this is a pretty standard question that you'll see pop up on the Algebra 2 exam. What you're looking for is, of course, a sampling method that allows you to basically get all types of students all over the place without getting any that are sort of in specialized categories. And the problem with 3 out of these 4 choices is that you're getting students in very specific categories. Like choice 1, we're getting only seniors, right? But then we're only going to know whether the seniors want to change the mascot. And they probably don't because they've been there for 3 years already. Right? Choice 2, we're going to only get people that are in art classes. Maybe the art students really are biased towards changing the mascot. I don't know. And choice 4, survey all members of the school's varsity sports teams. Well, now obviously we're only getting people on the varsity sports teams who probably would want to have the mascot stay the way it is. Not maybe all of them, but they probably have a bias towards it. On the other hand, choice 3, which is the correct choice, survey every fourth student entering the cafeteria during a lunch period. The premise here is that all students eat lunch, right? And therefore, we're going to get a broad cross-section by surveying every fourth student who comes into the lunch period. All right, so we're trying to find something that doesn't have any bias in it, and number 3 is the only one like that. All right, let's take a look at a problem that really gets into some nitty-gritty algebra in this course. Problem number 3. Given x not equal to negative 3, the expression 2x to the third plus 7x squared minus 3x minus 25 divided by x plus 3 is equivalent to which of the following? All right, now don't particularly worry about a statement like given x is not equal to negative 3. It can't be equal to negative 3 because that would force us to divide by 0, which we know we can't do. All right. So what do we need to do here? Well, we're going to do something called polynomial long division, and it looks a lot like normal long division. So here's how it works. I'm going to write down x plus 3, that should be a plus, and then I'm going to literally put down that classic division bar, okay? And I'm going to divide this into here. Now, the first thing I always ask myself is, what do I need to multiply x by to get 2x cubed? And that would be 2x squared. Then I'll take 2x squared, multiply it by x plus 3, and get 2x cubed plus 6x squared. All right, so this is very, very similar to the process of just normal long division, and I know most of you haven't done normal long division for a real long time. But now what I'm going to do is I'm going to subtract this from this. Now the easiest thing to do, instead of subtracting, is basically negating both of these things and add. Okay, and when I do that, the 2x cubes cancel, 7x squared plus negative 6x squared gives me x squared, and then I drop, just like I do in normal long division, I drop my negative 3x. At this point, yet again, what I do is I ask myself a simple question. What do I have to multiply x by? Don't worry about the plus 3. What do I have to multiply x by to get x squared? Don't worry about the negative 3x. Well, obviously, x times x will give me x squared, so I put plus x here. And again, now what I do is I take this x and I multiply it by x plus 3, and I get x squared plus 3x. Now again, it would be tempting to just add these two together the way they are, but if I did, the x squareds wouldn't cancel, right? So what I'm going to do is I'm going to negate both the x squared and the negative 3x, and I'm going to add them. All right, so I'm going to do this, and then instead of subtracting, I'm adding. These cancel. I have a negative 3x and a negative 3x, which is negative 6x, and I bring down my negative 25. Now I go back up one more time. I think to myself, what do I have to multiply x by in order to get negative 6x? That's going to be negative 6. All right, negative 6 times x is negative 6x. Negative 6 times positive 3 is negative 18. All right, yet again, instead of subtracting, the easiest thing for me to do is to negate both of these and add. So when I negate both of them, they become positive. Add. Those two cancel, negative 25 and positive 18 is negative 7. And now there's nothing else I can do. In fact, this is what's called my remainder. So at the end of the day, this division is all equal to 2x squared plus x minus 6 minus 7, all divided by x plus 3. All right? And what choice is that? That is choice 1. And again, I'd love to spend tons and tons of time on this problem, but that's the only polynomial long division we're going to be particularly seeing on this test, so it's time to move on. Let's go to the next problem. Problem number 4. In a group of 40 people, 20 have brown hair, 22 have blue eyes, and 15 have both brown hair and blue eyes. How many people have neither brown hair nor blue eyes? All right, fantastic. This is a problem that is well suited to what we call a Venn diagram. So this is what I'm going to do. A Venn diagram is basically you draw a rectangle and you put down your two categories and you label them as circles, okay? And those two categories are brown for brown hair and blue for blue eyes. Now, whenever I'm filling in a Venn diagram, the first thing I always do is fill in a number, if I have it, for the overlap. In other words, the people that have both brown hair and blue eyes. And they tell us that there are 15 people that have both of those. So I'm going to put a 15 in here. Now, they also tell us that 20 people have brown hair, right? 20 people have brown hair, but 15 of them are already accounted for. So there are an additional 5 out here, right, that have brown hair but aren't within the blue eye circle. Now, at the same time, 22 people have blue eyes, 15 of them are already accounted for, so 7 of them are in here, and those are the people that have the blue eyes but not the brown hair. Now, in total, right, when I add those up, 5 plus 15 plus 7, I get a total of 27 people that have brown hair, blue eyes, or both, right? But we had a group of 40 total people, so if I take my 40 and I subtract off the 27, what I find is that 13 people must be sitting here that don't have either brown hair or blue eyes. All right, I'm just trying to account for everybody. That's it. All right, let's take a look at problem number 5. Consider the function y equals h of x defined by the graph below. Then they give us another graph. Which equation could be used to represent the graph shown below? All right, now unfortunately this one's a little bit tough, so what I'm going to do is I'm going to reduce this kind of image size a little bit so that I can see both graphs. Maybe I'll try to zoom it in a little bit more than that. Let's see if we can get it at 150. Ah, we can. Okay, great, that's a little bit better. Now, what I should be able to tell immediately is that if this is my original graph, and that's specifically y equals h of x, this particular graph is simply the reflection of this one across the x-axis. So it's a reflection across x-axis. And the way that we do that each and every time, if I want to take a function's graph and flip it across the x-axis, what I'm doing is I'm simply multiplying all the values of the outputs by -1, right? Because when I multiply the y values by -1, then when I have a y value here of 4, it becomes a y value down here of -4. And so all this is y equals negative h of x. And that is choice 3. All right. Easy transformation question. At least I hope it is. All right. Let's take a look at problem number 6. For the polynomial p of x, if p of 3 is equal to 0, it can be concluded that which of the following? All right. This is an amazingly important idea in all of Algebra 2. All right. So first off, polynomials, right? Polynomials are things that kind of look like this. I'm just going to write down a random polynomial. Right? That's a polynomial, right? It's a combination of terms where all the terms have positive powers except for a constant term, etc. You've been studying polynomials for years, all right? But if I take a value and I substitute it into a polynomial and the end result is 0, right? That means that x equals 3, and let me just get rid of this because that's not our polynomial. X equals 3 is what's known as a 0. And any time I have a 0, then if I do x minus that 0, this then becomes a factor, right? It's what's called the zero product law. It's also an extension of what's called the remainder theorem in Algebra 2, all right? And the plain fact is, if the remainder is equal to 0, then x minus 3 must be a factor of p of x. All right, so it's basically if p of a is equal to 0, then x minus a is a factor. All right, and you've seen that time and time again, right? You know, and you use it especially when you factor something, right? And then you set each one of those factors equal to 0. So like if a factor is x minus 2, then x equals 2 is a 0. Or if the factor is x plus 7, x equals -7 is a 0. Here, we're kind of working that relationship in the opposite direction. If we know the 0, then we should be able to produce the factor. All right, let's take a little bit of a look at our first take on some exponentials and logarithms. Problem number 7. The solution to the equation 5 times e raised to the x plus 2 equals 7 is which of the following? And notice, of course, that all of the answers besides choice 3, which is clearly wrong, involve what's known as the natural logarithm. All right, so first I'm going to write down this equation so you can just see it a little bit better. 5e to the x plus 2 is equal to 7. Now, as always, when x shows up once and only once in an equation, I want to solve for x by simply applying inverses in the opposite order in which the original sort of operations were done to x. In other words, first I added 2 to x, then I exponentiated the result, and then I multiplied by 5. So to undo that, the first thing I'm going to do is divide both sides by 5. All right, that's going to give me e to the x plus 2 is equal to 7/5. Now, we're going to see this a couple times tonight. In order to undo exponentiation, I need to use a logarithm of the same base. So if this were 2 to the x plus 2, I would do the log base 2 of both sides. If this was 10 to the x plus 2, I would do the log base 10 of both sides. If this was 1.05 to the x plus 2, I'd do the log of 1.05, or base 1.05 of both sides. Here, I really want to do the log base e. Now, the log base e, all right, is just another name for the natural logarithm, all right? And I'll kind of replace that in a second. But anytime you have the same logarithm base as your exponent, those two cancel and you get this. Now, here's where I'm going to just replace log base e with ln because they are the same thing. So the natural logarithm and the logarithm base e are the same. It's unfortunate this was the first log problem we dealt with, but it is what it is. And now to finish it off, I just have to subtract 2 from both sides. All right, so x equals the natural log of 7/5 minus 2. Now, of course, they had to be a little bit irritating about this and write the answer down like this instead of this, which is just silly. But I hope that everybody here recognizes that choice 1, -2 plus the natural log of 7/5 is the same as the natural log of 7/5 minus 2. Whoo boy, let's take a look at a whopper of a multiple choice next. Number 8. Consider the system of equations shown below, and I'm not going to read off all those equations to you. What is the solution to the given system of equations? All right, now look. You learned how to solve systems of 3 equations with 3 unknowns in Algebra 2. I sure hope you did. It's still part of the curriculum. All right. Some of you may have even learned shortcuts on your calculators using things called matrices. All right. I'm not going to go into any of that. All right. That's not going to happen. The matrices, that is. All right. Because that would be different depending on what calculator you have. And I bet there's a good deal of students out there that never even learned that. All right. So you have 2 choices now. You can either try to solve this by simply taking a choice and plugging it into each one of these and seeing if it makes each one true, all right? And that is very legitimate, especially when you have 3 hours. Or you can do it the straight up algebraic way, which is what I'm going to show you right now in case something like this should come up in free response. All right, so here's the deal, right? What I want to do is I want to add equations together to try to get things to cancel out, all right? And one thing I notice right away is if I add, and I'm going to number these equations 1, 2, and 3. If I add equation 1 to equation 2, all right, it's going to produce a brand new equation for me, but what I should see is I have an x there and I have a negative x there. And when I add those two together, the x and the negative x will cancel, and I'll get 2y plus negative 3y, which will be negative y, negative z plus 2z, which will be positive z, and 1 plus 0, which will be 1. All right, so one thing is definitely true. If I take negative y and I add it to z, I have to get 1. Okay? Now, all by itself, right, just with that, You could then test this equation with all 4 of those choices and see which ones make it true and which ones make it not true. And if there's only one that makes it true, well, then that would be the right choice. But let's keep going because, again, I want to pretend this is a free response problem. Now, what I'd really like to do is add 2 more equations and have the x's cancel out, so I also just have the y and the z. Problem is, if I add equation 1 to equation 3, I'll get x plus 2x, and that'll be 3x. Those won't cancel. And if I add equation 2 to equation 3, I'll get negative x plus 2x, and that'll be just positive x. Also, the x's don't cancel. But one thing I could do is I could take equation 2 and I could multiply it by 2. So just for a second, I'm going to do this. 2 times equation 2. And what will that give me? That'll give me negative 2x minus 6y plus 4z, and 0 times 2 is still 0. Now, why did I do that? Well, when you solve systems of equations, you can multiply both sides of the equations by anything you want. You saw this back in Algebra 1, and you still get something very legitimate. Now the great thing is if I add this equation to equation 3, maybe I'll call this one equation 4. So if I add equation 4 to equation 3, let me put equation 3 just down here so we can see it a little bit better. Right? Now if I add these 2 together, what's going to happen is negative 2x and 2x will cancel. This will become negative 10y. This will become 5z. And this will become 10. All right, and maybe I'll call this equation 5. Now the cool thing is I've got these 2 equations, and maybe I'll call this equation 6 up here. Equation 6 and equation 5 only have y and z in them. All right, so they should be pretty easy to solve. Now, how do I want to solve them? Well, again, I want to add them together and have something eliminate. Well, again, nothing's going to happen right away because negative y plus negative 10y is negative 11y. Z plus 5z is 6z, so they don't cancel. But what I could do is I could take equation 6 and I could multiply everything by negative 10. Right? So if I take equation 6 and I multiply it by negative 10, then what that's going to give me is positive 10y minus 10z is equal to negative 10. All right, maybe I'll call that equation 7. That's right, I did rewrite that as equation 7. All right, now what I'm going to do is I'm going to add these 2 equations together, 5 and 7, and that's going to eliminate the y's. Negative 10y plus 10y goes away. 5z and negative 10z gives me negative 5z, and 10 plus negative 10 gives me 0. I can now easily solve this equation for z, and I get z equals 0 divided by negative 5, so z is equal to 0. All right, and now that is truly enough to figure out what the right choice is, because when I look at all of these pairs, and remember it's x comma y comma z, the only one where z is equal to 0 is right here. Now again, pretending for a moment this is a free response question, not a multiple choice question, so you have to produce both the value of y and the value of x, we could now take the value of z and let's say plug it into this equation, right? And that would give me negative y plus 0 is equal to 1. That would be negative y is equal to 1, and y would be equal to negative 1, which again tracks with what I have right here, right? And then if I wanted to figure out what x is, I could take both the z equals 0, the y equals negative 1, and plug it into any equation I want that has all 3 in them. Probably the most convenient one would be the first one, right? And then I could say x plus 2 times y minus z is equal to 1, and that would be x minus 2 is equal to 1, and x would be equal to 3. So again, I realize that there are other ways to do this, but that's the way you full on do this particular multiple choice problem. All right, that might be the longest multiple choice problem we see tonight, but then again, there is number 9. Let's take a look. Monthly mortgage payments can be found using the formula below, where M is the monthly payment, P is the amount borrowed, R is the annual interest rate, and N is the total number of monthly payments. If Adam takes out a 15-year mortgage borrowing $240,000 at an annual interest rate of 4.5%, his monthly payment would be which of the following? Oh my goodness. Okay, well, this is really an issue of can you plug stuff into a formula correctly? And also, do you understand the rate, all right? So we know what P is in this formula, all right? And in fact, let me just I'm gonna zoom this thing in a little bit more so that we can see the formula a little bit better, right? So we know that P is 240, all right? So one thing for certain, P is 240,000. All right, so we got the P, all right? Now the R is a little bit tricky. And it's a little bit deceiving because they use the terminology. You might think R is 4.5, but it's not, okay? Anytime an R, a rate, shows up in one of these types of interest problems, it's always the decimal version of the rate. So R is 0.045. Whoops, come on. Where is? Jeez, man, talk about the delay. Let me try that one more time. There we go. Okay, so R is 0.045, all right? And the final piece is the N. The N is the number of monthly payments, the number of monthly payments. But that's going to be N is equal to 15 times 12, right? Because you've got 15 years, you've got 12 payments per year, and therefore N, when we do that multiplication, is 180. All right, so now the issue is we just got to plug all this stuff in to this particular formula. And this is the way it's going to look, right? I mean, it's going to look like 240,000 times 0.045 divided by 12 times 1 plus 0.045 divided by 12, all raised to the 180, all divided by 1 plus 0.045 divided by 12 raised to the 180 minus 1. Whew. And I just got to hope you can get that in your calculator correct. So let's take a look at it, right? All right. Now, it's ugly, right? But on the TI Inspire calculator, it's actually not too bad. It's not too bad. Now, I'm not sure if I can actually move this to the extent where you can see it all. It doesn't look like it. But let's take a look at it. So I'm going to put that fraction bar up. I've got my 240,000, all right? And I'm going to do fractions within fractions, okay, because I've got 0.045 divided by 12, all right? Now I've got my 1 plus, again, 0.045 divided by 12. And that's all raised to that 180. All right, that's the number of monthly payments. That's my numerator. My denominator, 1 plus, again, my fraction, 0.045 divided by 12, raised to the 180, and then minus 1. So before I hit enter, right, that mess is all of this. All right, and it's just about being patient, putting the formula in, making sure you know what all your values are, and then hitting enter and hoping, right? So my payment is monthly payment $1,835.98. And that is right here. All right, that is an ugly problem. But at the end of the day, right, strangely enough, there's not that much math in it, right? It's about plugging numbers in your calculator. Don't get me wrong, there is some math, right? The math being to recognize that I'm not to use 4.5, but 0.045. You know, figuring out the number of payments based on the fact that there are 12 months in a year, obviously, and there's 15 years, so 15 times 12, okay? But that's about it. Now let's look at one that's kind of cool and definitely has some math in it. All right, let's take a look at problem number 10. Sorry. For all real values of x, if f of x is equal to x minus 3 quantity squared, and g of x is equal to x plus 3 quantity squared, what is f of x minus g of x? All right, I actually really like this problem. I think it's cute. I don't know if that's the right way to put it, but I'll call it cute. I'm going to actually go down here to do it, just to give myself a little bit more room. We're not going to need almost any room for number 11. So they want f of x minus g of x. So the first thing I'm going to do for myself is I'm going to write down what that is. Right? Now, it would be great, obviously, if that was just randomly one of the answers, but it's not, obviously, right? Now, it could be that your first instinct would be, okay, let me FOIL all of this out and FOIL all of that out, and then let me combine like terms and things like that. And that would work, okay? No question about it. But the cool thing about this expression is it has the structure of difference of perfect squares. In other words, right, if I have something that looks like a squared minus b squared, then that, right, can be written as a plus b times a minus b. Okay? And I point this out because the a can be x minus 3 and the b can be x plus 3. In other words, this, right, recognizing structure to factor, I can write down as x minus 3 plus x plus 3 times x minus 3 minus x plus 3. All right? And now let's do some simplification. First, let's deal in here. This one's easy, right? There's nothing that these parentheses are particularly doing here because there's no subtraction going on. This one's a little bit worse, though, the second set, because I have to distribute that subtraction through that binomial. The first set of parentheses isn't doing anything, but the other one I have to basically do that with. I have to distribute that subtraction. Now let me do a little bit more simplification. This first one, right, the negative 3 and the positive 3 will cancel, and I'll just be left with 2x. In this particular problem, the x and the negative x will cancel, and I'll just be left with negative 6. Oh, how nice is that? And 2x times negative 6 is negative 12x. And that is choice 3. And that is really the way they expect you to do the problem. They expect you to recognize that because I've got something squared minus something squared, I can actually factor it into the difference of perfect squares, and that makes it far easier to simplify than multiplying all this out using FOILing or whatever technique you use, same here, and then doing the subtraction. Again, that'll work, and you'll get negative 12x, I promise you. But it will take longer, and there's more chance for errors. Okay, let's go up to number 11. If f of t equals 50 times 0.5 raised to the t divided by 5,715 represents the mass in grams of carbon-14 remaining after t years, which statement must be true? 1, or I guess, letter I, the mass of carbon-14 is decreasing by half each year, and 2, the mass of the original sample is 50 grams. All right. Well, and then it's 1 only, 2 only, 1 and 2, or neither 1 nor 2. All right. Again, what I'd like to do is just make this a bit bigger so that we can see this particular expression, maybe even make it bigger. Let's go 400. Oh, yeah. Yeah, I'm loving it. Okay. Now, one thing I can tell you is immediately true is number 2. How do I know that? Well, if I put t equals 0 in here, 0 divided by 5,715 is 0. 0.5 raised to the 0 is 1, as anything is raised to the 0, except for 0. And 50 times 1 is 50, right? And that's classic. In exponential modeling, almost always, the number sitting out here is the original size of the whatever. The original size of the investment, the original size of the radioactive material that's decaying, which is what's going on here, the original population of llamas, whatever it is, right? So the mass of the original sample is most certainly 50 grams. Now the question is the mass of carbon-14 decreasing by half each year? Well, the question is, every year do I get to multiply by 0.5? And the answer is no, right? In fact, I only get to multiply by 0.5 to the first after 5,715 years, right? So every 5,715 years, the mass of carbon decreases by half. Okay, but not every year. That is definitely not the case, and so it is choice 2 only. All right, let me go back and fit width, fit width. That sounds funny. All right, let's take a look at number 12. Consider the graph of G and the table representing T below. So I've got G of X and T of X. I hate it when they use T as the name of a function. It's almost always an input variable. Anyway, whatever, that's just me. All right, so then the question states, over the interval 2 to 4, which statement regarding the average rate of change for G and T is true? All right, so this is all about the average rate of change of these two functions on the interval 2 to 4. So what I want to do, not surprisingly, is calculate the average rate of change for the both functions on the interval x equals 2 to x equals 4. So for the one that's presented graphically, what I want to do is go here to this point, and that's the point 2, 1, 2, 3, 4, 5, 6. And then I want to go over here to the point 4, 10. Here it's going to be way easier because here's my 2 and here's my 4, right? I don't need to worry about those too much. Now let's calculate the average rate of change for G. So delta G over delta X will be 10 minus 6 over 4 minus 2, which will be 4 halves, which is 2. So the average rate of change of G of X over that interval is 2 to 1, or just 2. Now for T of X, right, so the change in T over the change in X is going to be 3 minus negative 5 all over 4 minus 2, which is going to be 8 divided by 2, and there's my red pen making its first cameo appearance of the night, and I get 4. Right? So what I see is obviously, right, the two average rates of change are not the same. Let's see, the first choice is G has the greater average rate of change. Well, that's not true. Its rate of change was 2, right? So again, for G, it was 2, and for T, it was 4. Okay, I don't want to say G equals 2. I'm just, 2 and 4. The average rates of change are equal. No, that's not true. The average rate of change for G is twice the average rate of change for T. Nope, right? That's 2 and 4. It's the other way around, right? Number 4, the average rate of G is half the average rate of change of T. There's our winner, right? 2 is 1/2 of 4, and therefore that is our answer. All right. Let's take a look at one more problem, then take a little break so I can get a drink of water. Or, actually, lemonade. Number 13. A parabola has a directrix of y equals 3 and a vertex at 2, 1. Which ordered pair is the focus of the parabola? Wow. Okay, so one of the things that you studied, hopefully for no more than 1 or 2 days, is what's called the locus definition of a parabola. All right, and I don't want to go into this too much, but it's this idea, right? We can actually define all the points on the parabola by some kind of a line, which is called the directrix, and what's known as a focus. All right? Now, how do you then define the points on a parabola? Well, the points on a parabola will be all the points that are equidistant, the same distance from the focus as they are from the directrix. And the vertex is the easiest point of all because it is literally halfway in between. And then what happens is that all the other points kind of get mapped out in some given way. Okay? So let me just be very clear. That's the focus. Here's the vertex. And we have the directrix. All right? So now let's take a look at what they've told us. Okay? So for our actual problem here, what we know is that we have a directrix of y equals 3. All right? So y equals 3 is our directrix, and we have the vertex point at 1, 2, 1. So that's actually the vertex. All right? Meaning, right, that the parabola actually kind of looks something like this. All right, and remember that vertex has to be equidistant between the directrix and the focus. Well, it's 2 units away here, And therefore, we need to go 2 units down here, and that is going to be at 2, -1. And that is where our focus will be. At least for this problem, that's where our focus will be. All right, see what I did there? Let me just get to the next page, and we'll just take a little bit of a break before we do some calculator work. All right, doing well, a little bit past the half-hour mark. Algebra 2 makes me thirsty. That's all I'm going to say. Algebra 2, it makes me thirsty. All right, so we're working through the multiple choice problems. All right, so far we've gone through 13. I think there's a total of 24, so we're a little bit more than halfway on the multiple choice problems. We've seen some problems that are just straight up kind of algebraic, all right, and we're going to see our real first sort of statistics problem where we're definitely going to have to use our calculator coming up in number 14. Let's take a look. The heights of 3,300 students at Ocean View High School are approximately normally distributed with a mean of 65.5 inches and a standard deviation of 2.9 inches. The number of students at Ocean View who are between 64 and 68 inches tall is closest to blank. All right, great. So you should have learned about the normal distribution. And the great thing about the normal distribution is that on the calculator, right, the calculator will tell you the percent of a population that lies between any two given values if you know the mean and the standard deviation of that population. So just really quickly, let me kind of get this out. All right, so I'm going to go to my calculator, and again, this will very much depend on your calculator. All right, but all the Texas Instruments calculators kind of work the same. I'm going to hit my menu button. All right, I'm going to go down to choice 6 for statistics. And then what I want is choice 5, what are called distributions. Now it's kind of tricky because there's two normal distributions. There's the normal PDF, which basically, let me just say right now, you're never ever going to use. Okay, I don't even know why they have it on here, and it really annoys me that it's the first one. But anyway, right, what we want is the normal CDF. Now, they say, what is the lower bound? Now, the lower bound is going to be the first data point that you sort of want the percentage between. So they say we want it between 64 and 68 inches. So my lower bound is 64 inches, all right? My upper bound is 68 inches. That little weird Greek character is what's called mu, and that's actually the mean, 65.5. And then sigma is the standard deviation, that's 2.9, all right? So my lower bound, my upper bound, my population mean, my population standard deviation, and when I hit OK, it spits out this long decimal. And that is literally the proportion of the population that lies between those two values. In other words, about 50.3% of the population lies between 64 and 68 when you have that mean and standard deviation. But that only gets us so far. We actually want to know the number of students, right? So what we need to do is we need to take that proportion, 0.50318, and we need to multiply it by 3,300, and that is just about 1660. All right, very calculator driven. There is literally no way to do this problem without a calculator. Talking about calculator problems, let's take a look at number 15. Which statement below about the graph of f of x equals negative log of x plus 4 plus 2 is true? All right, and then they give us just a bunch of different sort of like f of x has a y-intercept of this, negative f of x has a y-intercept of that, etc. I want to do a little like closer zoom on this just so I can sort of see these choices. Oh, I like that 300%. That really blows the problem up. I might keep it there. Anyway, so, you know, one thing that you want to do on this problem, if it's not immediately obvious, and even for somebody like me, this is not necessarily immediately obvious, is you just want to graph the thing. All right. Now, one thing that's key is that here we have a logarithm that with no base written, all right, which means it's base 10. Now, some of you, right, especially those of you using, let's say, the TI-83 or TI-84, there is just a log button with no base on it, and that is log base 10. That is what we're working with here. On the TI Inspire, actually, you're at a little bit of a disadvantage here because you need to know that that's log base 10. But let's just take a look at the graph of this. Okay, let's just see what it looks like and see if we can kind of make sense of our choices here, all right? I'm just going to flip over to my graph, all right? And what I want on this is I want negative log, and again, I have to put in the base 10 here, and that's going to be x plus 4. I got to get out of the parentheses plus 2. All right, so there's my function. All right, again, I have to know it's base 10, although, to be honest, no matter what base you put in there, as long as it's a number greater than 1, you're probably going to get the right answer. And I hit enter. Okay, so there's my function. Right? Now, what am I seeing here? Well, one thing I can see right away is that the y-intercept is between 1 and 2. Between 1 and 2. Okay? Now, if I look at my choices, right, it says, well, f of x has a y-intercept at 0, 2. Well, it doesn't. It's somewhere between 1 and 2. Then it says negative f of x has a y-intercept of 0, 2. Well, that's also not true, right? I mean, that would be if I took the graph and I flipped it over the x-axis, but if I did that, then it would have a y-intercept down here at like negative 1.5, roughly, right? Because there's 1 and there's 2. So both of those things are wrong. All right, now notice, as I move this way and I get closer and closer to x equals negative 4, what's happening is the graph is headed up towards infinity. So we would say that as x approaches negative 4, f of x approaches infinity, right? It's kind of going uphill. As we kind of get closer and closer to negative 4, this thing kind of skyrockets up that way. And in fact, there it is. As x approaches negative 4, f of x approaches infinity. All right. By the way, if you look at choice 3, as x approaches infinity, f of x approaches infinity. Well, that is definitely not right, because as x approaches infinity, which is way out here, the y value is actually getting smaller and smaller, right? So, you know, if as x approaches infinity, f of x approaches infinity, we're going to expect this graph to be going up as x goes to the right, and that didn't happen. All right. Go back there, and let's take a look at another statistics question. A researcher wants to determine if room darkening shades cause people to sleep longer. Which method of data collection is most appropriate? 1, a census, 2, a survey, 3, an observation study, and 4, a controlled experiment. All right, so let's talk about like what these different things are. A census is literally when you ask every single member of the population to answer a particular question, all right? Well, that's not going to happen, right? Census is censi? I don't know what the plural of census is. Anyway, that's not the point. The point is, if you do a census, it's very rare, right? It's very, very rare, and it's never going to happen here because we'd really want to know all people, right? So that's not going to happen. All right. Now, a survey might not be terrible, but for a survey, what you'd literally have to do is you'd have to kind of like call people and you'd have to say, hey, do you sleep with room darkening shades? Okay, well, great. How long do you sleep? You know, so that might be okay. It would certainly get us some data, right? But I don't know, does it really cause people to sleep longer? Maybe people who sleep longer just buy room darkening shades. Do you know what I mean? Maybe the darkening shades don't actually cause them to sleep longer. So I don't know. That one seems sketchy. An observation study, that's one actually where it's sort of like, okay, we would just find out that there are people with room darkening shades, right? And then we'd observe how long they sleep. Okay, but we would have no control over who gets the shades and who doesn't get the shades. And finally, a controlled experiment. This is when we would gather maybe 100 people, and we would randomly assign them to two groups. One group, we would say, okay, you're sleeping with room darkening shades, and the other group, we would have them sleep without room darkening shades, and then we would just see which one of them slept longer. And there's your winner, right? Because with a controlled experiment, meaning that you have a control group, right, that doesn't get the shades, and a non-control group, a treatment group that does get the shades, right? You could then look at the data and see, well, is there a statistically significant increase in the amount of sleep a person gets if they're assigned to the group that gets the room darkening shades? Definitely a controlled experiment. All right, let's take a look at 17. I do like the zoomed in look. The inverse of f of x equals negative 6x plus 1/2 is which of the following? All right, they love giving you a linear function and asking you for its inverse. And this one is particularly obnoxious because of the 1/2. Yet, it's still done the same way. Anytime they give you an equation and they ask you for the inverse equation, the first thing I want you to do is I want you to switch the roles of x and y. Okay, in other words, right, f of x is just the same thing as y. So I'm just going to replace the y with x and the x with y, and now I'm going to solve for y. Okay, so the first thing I'm going to do is I'm going to subtract a 1/2 from both sides. All right, like that. And now I know that everything in you is saying, oh, I should definitely just divide both sides by negative 6. And I totally would get that, and that sounds great. But I don't see anything in here that looks like x minus 1/2 divided by negative 6. You know what I mean? I just don't see that as one of the choices. So what I'm going to do is instead of dividing by negative 6, I'm going to multiply both sides by negative 1/6. Okay? And negative 6 and negative 1/6 will cancel. And I'll get y equals negative 1/6 times x minus 1/2. Okay? And we're getting there. We're getting close, right? But now what I'm going to do is I'm going to distribute that multiplication by negative 1/6. And I'll get negative 1/6 x, and now negative 1/6 times negative 1/2 will be positive, and then, hey, multiply fractions. Multiply their tops, multiply their bottoms, and there is the equation of the inverse. All right? No matter how ugly it is, this method will always work. Switch x and y and solve for y. Okay, let's take a look at number 18. The expression x squared plus 12 divided by x squared plus 3 can be rewritten as blank. All right, well, believe it or not, this is a very easy version of polynomial long division that we saw earlier. And we could actually do this with polynomial long division. But there's an easier way to do it. You know, notice, right, and I'm going to rewrite it like this. Right? Notice that x squared plus 12 and x squared plus 3 are very similar. I mean, like, very similar, right? To the point where, you know, x squared and x squared plus a number plus a number. In fact, I could rewrite the numerator as x squared plus 3 plus 9, and then I think I'll just leave the denominator as x squared plus 3. Now, addition is associative, meaning that I can really think about this like this. All right? And my final little piece is that division is distributed. So I can then rewrite this as x squared plus 3 divided by x squared plus 3 plus 9 divided by x squared plus 3. All right? So all I've done is broken up x squared plus 12 so that it looks like x squared plus 3 plus something, or minus something, but in this case it's plus something. And now x squared plus 3 divided by x squared plus 3, hey, anything divided by itself except for 0 is equal to 1. Anything. 5 divided by 5, negative 10 divided by 10, cow divided by cow, I don't care. Anything divided by itself except for 0 is equal to 1, and therefore all of this is equal to 1 plus 9 divided by x squared plus 3. And that is choice 2. Okay. Moving on. All right, number 19. I'm going to make this one a little bit smaller so that we can see the whole question. An angle theta is rotated counterclockwise on the unit circle with its terminal side in the second quadrant. I love that. The angle isn't rotated, the ray is rotated. If an angle is rotated, anyway, never mind. An angle theta is rotated counterclockwise on the unit circle with its terminal side in the second quadrant as shown in the diagram below. Which value represents the radian measure of angle theta? All right, I don't know if this is tricky or just extremely easy, okay? But you should have learned something very specific in both geometry and Algebra 2, which is that the radian angle measure of any angle, whether it's on the unit circle or not, is equal to the arc length intercepted by the angle or subtended by the angle divided by the radius. So this is the arc length divided by, obviously, the radius. Well, in this, it doesn't really get any easier than this, right? The arc length that is intercepted by the angle is equal to 2, not 2 pi or anything like that, just 2. The radius is equal to 1, so the radian angle is equal to 2. Now, I think what they're getting at here is that if you're on the unit circle, the circle with a radius of 1, the basis of all the trigonometry in this particular course, right? Then the radian angle is simply equal to the arc length. Theta and s are the same on a unit circle. Maybe that's what they're getting at here. I don't really know. You know what I mean? I'm not even sure what the rest of the answers are supposed to be about. All right, let's take a look at number 20. The depth of water, d of t, in feet on a given day at Thunder Bay, t hours after midnight, that's real key, is modeled by d of t equals 5 times the sine of pi over 6 times the quantity t minus 5, all plus 7. Which statement about Thunder Bay tide is false? All right, well, I'd like to talk about this model a little bit more now. Okay, so this is really kind of our first chance at looking at what's called a sinusoidal model, and these will come up a few times on this particular exam, so let me take a little bit of a moment to discuss it. And for the moment, let's not worry about the pi over 6 or the t minus 5. Let's just talk about the 5 and the 7, right? The 7 is what's called the midline, all right? And the 5, or at least the absolute value of the 5, is called the amplitude. All right, and in trigonometric modeling, the idea is you've got this midline at 7, and it's going to go 5 above and 5 below, 5 above and 5 below. All right, so one thing I can tell you right away is that the maximum value is equal to 7 plus 5, or 12, and the minimum value is equal to 7 minus 5, and is 2. So right away, I can tell you that the maximum is 12 and the minimum is 2, right? But then there's a lot of other stuff on here that gets a bit confusing, although even those two alone are enough to pick out which one is not true, right? Which statement about Thunder Bay tide is false? But regardless, what I'd like to do is put this into our calculator, all right? So let's take a look at this thing in our calculator. You've got 3 hours. It never hurts to graph, all right? So I'm gonna open up a brand new file here. New, no, not worry about it. I'm gonna add a graph. All right, so here we go. I'm gonna have 5 trig times the sine. I'm gonna put the fraction bar in of pi over 6 times, now I'm going to use x instead of t, but that should be comfortable for you, I hope. All right, that plus 7. All right, now, I've got a little bit of a problem right now, and we'll discuss it in a moment. I'm going to hit enter, just to kind of have it there, right? I don't really see much of anything, all right? Now, there's a couple reasons for that. One reason is because my window isn't so great, but the bigger reason is this little DEG sitting right here. All trigonometric modeling in Algebra 2 with these types of equations is done in what's called radian mode. Radian mode. Not degree mode, but I'm sitting in degree mode because yesterday I was reviewing the geometry Regents exam, and there you do a bunch of right triangle trig where all the trigonometry is in degrees, all right? But this is in radians. Now for me it's as easy as just tapping on that, and now I have radians. Now let's start to play around a little bit with the window. Now remember, t represents the number of hours, or x represents the number of hours since midnight. So it makes sense that if I'm going to play around with the window, so let me go into Menu, Window, and my window settings, I'm going to have my hours go, let me just go 0 to 12 for right now. Maybe I should go 0 to 24. I'm just going to go 0 to 12 for the time being. Now, I know that my minimum is 2 and my maximum is 12, so I think I'm going to put my minimum at 0 and I'll maybe put my maximum at 15 and I'll hit enter. And look at that, right? Makes so much more sense now, all right? And I can start to think about all the different choices, right? One of the choices, right, was low tide occurred at 2 a.m. In other words, the lowest level occurred at 2 a.m., right? Well, does that occur at 2? Well, one thing that I could do is I could go into my menu, I could go into Analyze Graph, I could look for the minimum, right? I'm going to bring this thing kind of to the left of the minimum, hit enter, bring it to the right of the minimum, hit enter, and it looks like the minimum occurs at 2, at 2 a.m. Because remember, X is the hours after, right, midnight. Now, so that one's correct, all right. We already know that the maximum depth of water was 12 feet, so that one was cool. The water depth at 9 a.m. was approximately 11 feet. Well, this is a great chance, right, if we're right here, to hit Control T and throw a table in. And what did I want? I wanted to see what the level was at around 9 a.m. So that's 11.33 feet, and it said approximately 11 feet. I'd say, yeah, okay, that's good, right? So finally, it seems like maybe the right choice, which is the wrong thing, right? Because I'm looking for the thing that's false. It says the difference in water depth between high tide and low tide is 14 feet. While high tide, the depth is 12, low tide is 2, so the difference is actually 10 feet, not 12 feet, and so that's the wrong answer. By the way, the difference between the high and the low will always be twice the amplitude. The amplitude is how high up above the midline and how low below the midline you go. So if you go 5 above and 5 below, the difference between the high, the max, and the low, the min, will always be twice that, or 10. So I could have really gotten that right away, but I wanted to take advantage of the fact that I could, do a little bit of graphing. All right, let's look at one that looks awfully ugly. 21. A function is defined as a sub n equals a sub n minus 1 plus log base n plus 1 of n minus 1, where a1 equals 8. What is the value of a sub 3? All right. Now, I really wish that they had just said, instead of a function, they had said a sequence is defined recursively as, because that's what we have here, right? A recursively defined sequence, all right? Now, all we have to do is be careful about our subscripts. Now, we want a3, and we can't get that before first finding a2. So let's write down what a2 should be. a2, now again, that's n equals 2, right, is equal to a of n equals 2 minus 1, so that's a1, plus log base n plus 1, that should be 3, of n minus 1, which is 1. So again, right, if n is 2, then that subscript is 1, that subscript is 3, right, and then that is 2 minus 1, which is 1. All right, now we just need to fill in some numbers. So a2 is equal to 8 plus log 3 of 1. Now, it'd be great if you knew what log base 3 of 1 is. In fact, the log base anything of 1 is 0, because what logarithms do, this is the first time we've really discussed what logarithms do, is logarithms give you the exponent you need to raise this number to in order to get that number. Let me say that again. Logarithms are the number we have to raise this number to in order to get that number. Now, say you don't understand that, well, then you could always just take the calculator out, right? You go back to this calculation and you say, what is 8 plus log base 3 of 1? And we get 8, because log base 3 of 1 is 0. All right, so we get 8. Great. Now let's get a sub 3. a sub 3, right, is going to be a sub 2 plus log base 4 of 3 minus 1, which is 2. So a sub 3 is going to be 8 plus log base 4 of 2. Now, this is kind of cool. We'll do it on the calculator in a moment, but what do I have to raise 4 to as an exponent in order to get 2? Well, that's 1/2, right? Because the square root of 4 is equal to 2, right? That is log base 4 of 2 is 1/2, because 4 to the 1/2 is equal to 2. Again, if that's a little bit too much right now, because it's, late on Monday night, then we can always do this. And we get 8.5. By the way, I'd be remiss in not mentioning the fact that it is Juneteenth, right? Freedom Day. Right? And just as a little mention of that, right? You're getting this day off. It's a national holiday, right? And it's a day when we celebrate, and I'm sure you all know this history probably much better than I do, so I apologize to anyone that I botched it a little bit on. But Juneteenth is a celebration of when a Union general went into Texas and brought the Emancipation Proclamation into Texas, effectively freeing the last enslaved people in this country, right? And it happened on, I think, June 19th, 1865 or something like that. And I'm bad about that, and I apologize. But that's what today is all about. We get lots of days off from school all over the place. Many of them are very, very worthy days. Some of them are certainly questionable, right? But the day when we officially ended slavery in this country, I think is a fantastic day to celebrate. So I'm glad you had the day off, but I hope you also take a little bit of a moment to think about why you get this day off. It's really kind of great. Anyway, let's keep going. All right, 22, which I'm going to make a little bit smaller so that we can see it. Here we go, 22. Which function has a maximum y value of 4 and a midline of y equals 1? All right, well, this one I thought was a very strange question because we really never talk about the midline for really any graphs other than sine and cosine graphs, right? In sine and cosine graphs, we talk about midlines because the graph oscillates, goes above and below a given horizontal line called the midline. All right, so it's weird to me that we would even talk about midlines with these two choices because they're not trig graphs. Now, don't get me wrong, maybe there's somebody out there that would say, well, let's say you had some kind of cubic graph like this. Maybe something like that is its midline, but I don't buy it. I just don't, right? A midline literally is a piece of terminology that we reserve for trigonometric functions. So, right, these two. Now, we already talked a little bit about midlines. Midlines are simply y equals this number. And in both of these two problems, or both of these two choices, the midline is in fact y equals 1. So the real question becomes which one of them has a maximum y value of 4? Well, it would be tempting to choose this one because it's y equals 4 sine x plus 1. But that 4 is the amplitude. We were just talking about that with the tides problem, right? That is the amount you go above and below the midline. So in fact, the maximum value here is 1 plus 4 is 5, okay? So that's not the right choice. In fact, it's this choice, right? And here, the amplitude is equal to 3, all right? So we are going 3 units above 1 and 3 units below 1, so the maximum value in this case is 1 plus 3, or 4. So there we have it. All right, great. Let's take a look at our first complex calculation of the night, 23. Which expression is equivalent to x plus yi times x squared minus xyi minus y squared, where I is the imaginary unit? All right, well, one of the reasons that they give you such an ugly problem like this is that so much complex arithmetic can be simply done with the calculator. So if they give you something like 5 minus 3i times 8 plus 2i, you can just plug that in your calculator and it's going to give you the answer. So they like doing something like this, which is much harder to use your calculator on. Again, let me just kind of zoom in a little bit on this, hopefully. All right, there we go. So let's take a look at this product. Now, all by itself, even if I wasn't the imaginary base, this would be a little bit of a challenging problem because we've got a binomial multiplying a trinomial. And one way that I love doing this is with an area model. All right, I'm going to just maybe move my little icons here out of the way. And by an area model, what I mean is I'm going to draw out a rectangle like this. All right, and I'm going to make it a 2 by 3 rectangle, and I'm going to put x and plus yi here. And here I'm going to put x squared minus xyi and minus y squared. And now what I'm going to do is I'm going to fill in all the boxes with just the products. For instance, x times x squared will leave me with an x cubed here. X times negative xyi will leave me with negative x squared yi. And x times negative y squared will leave me with, well, negative x times y squared. That was weird. Now, yi times x squared will leave me with x squared times yi. yi times negative xyi will be negative x y squared I. Come on. Nope, just doesn't want to do it. There it goes. I knew that was going to be the delay. I squared. Come on, I need that to look like a squared. And yi times negative y squared will be negative y cubed I. All right. Now, let's take a look at what we can combine, what we can cancel, etc., etc. Nothing will combine with the x cubed. All right? Now, oftentimes when things do combine in this type of product, they're along the diagonals. Now, notice here we have negative x squared y times I, and here we have positive x squared y times I. So those two, when added together, will simply cancel. Now, here's an interesting one because we have negative x times y squared times I squared. And that is the only time this whole imaginary thing is going to come into this problem, because the thing we're supposed to know is that I squared is equal to negative 1. All right? I squared is equal to negative 1, which means I can replace that I squared with a negative 1. All right, this becomes negative 1. And if that becomes negative 1, then all of this becomes positive x squared y. And that positive x squared y cancels this negative x squared y, and the only thing we have left is y cubed I, and that is choice 4. All right, cool. Let's do our last multiple choice problem. All right, number 24. The growth of a $500 investment can be modeled by the function p of t equals 500 times 1.03 to the t, where t represents the time in years. In terms of the monthly rate of growth, the value of the investment can be best approximated by which of the following? Okay, I hate this problem. They have this problem all the time. And believe it or not, this problem, even though it would just never ever come up this way in the real world, this problem still relies on that exponent property that we saw originally, which is x to the m to the n is equal to the x to the m times n. But we are going to apply it in the sneakiest of ways. Now, one thing I don't want you to forget is that t represents the time in years, and it will always represent the time in years. They can't decide to change what t represents. T can't suddenly become the time in months, all right? But keep in mind that if I had the monthly rate, I would want, which I don't know yet, but if I had the monthly rate, I would want to raise it to the number of months that had passed. And the number of months will be the number of years times 12. So what I'm going to do is I'm going to take my model, p of t equals 500 times 1.03 to the t, and I'm going to rewrite it in a tricky little way. All right, what I'm going to do is I'm going to multiply, all right, my t by 12, but then I'm going to put a 1/12 in here. All right, So why do I do that? Well, number one, 1/12 times 12 would be 1. According to this, according to that exponent law, that would be the same thing as just having it to the t. But now this represents the number of months that have passed, because the number of years, t, times 12 would be the number of months. And that means 1.03 to the 12th must represent the monthly rate. Well, let's see what that is really quick. Like, what is 1.03 raised to the 1/12th? Well, that's 1.00246, etc., or 1.00247, let's say. So that's 500 times 1.00247 raised to the 12t, and that is choice 1. They love this problem, going between years and months. And the way that you do that is you multiply the number of years by 12, but then you raise your base to the 1/12, all right? And you're really kind of employing this exponent rule, but again, in this direction, right? You're really going in that direction. You're taking just a single t, and you're making it into 1/12 of 12t. Right? Which is weird. You'd be like, well, why do I want to do that? Well, again, it's to make sure I'm raising it to the number of months I have, but then this becomes my monthly rate. All right. I believe that might be it for my multiple choice problems, and it is. All right, so now we're going to move on to our part 2s, which means it's time to take a little bit of a lemonade break. Ah, lemonade. This is my third Regents review, obviously, right? We did Algebra 1 last week. It seemed like a lifetime ago. I think it was last week, Tuesday or Wednesday. All right, last night we did the geometry review. And those of you who are taking the geometry exam tomorrow, I would question why you're watching the Algebra 2 review tonight. But if you are taking the geometry exam tomorrow, good luck. And you can still catch our geometry review. It's housed now on YouTube. For those people who are taking the Algebra 2 exam in a couple days, which I assume is most of you, keep in mind that this review will be posted to the eMath Instruction YouTube channel under the live video section, and it'll be posted probably, I think it's within a half an hour. It's probably even less than that. It'll be posted right after we're done filming. All right? All right, so we just did 24 multiple choice problems worth 2 points apiece with absolutely no partial credit possible. All right, now we're going to move into the part 2 questions, which are also worth 2 points apiece. There are only 8 of them, only 1/3 of the number of the multiple choice questions you just had. But here they're free response, which means you could have a chance for partial credit. All right, and we're going to start to work on them right now. So let's take a look at problem number 25. Does the equation x squared minus 4x plus 13 equals 0 have imaginary solutions? Justify your answer. Well, one way to do this problem is to simply find the solutions. And the way that you would find the solutions typically, especially if you think they could be imaginary solutions, is by using our friend the quadratic formula. You really can't use anything besides that or completing the square in order to get imaginary solutions. Now, I really don't even have to solve for the solutions. One of the things I hope that you learned was that this quantity underneath here, b squared minus 4ac, known as the discriminant of the quadratic, that's what controls whether or not my roots are real or imaginary. If that thing is negative, well then we have to take the square root of a negative number and we're going to have imaginary roots. So if the question is just, do we have imaginary solutions? All you have to do is calculate this number. If that number is negative, you're going to have imaginary solutions. And if that number is 0 or positive, i.e. not negative, then you're going to have real solutions. So let's take a look. Right? B squared will be negative 4 squared minus 4 times 1 times 13. And when I work all of that out, what I find is that the discriminant is equal to negative 36. And because the discriminant is negative, we will have imaginary roots. Yes, because the discriminant is negative. You probably wouldn't even have to write out that statement. As long as you showed b squared minus 4ca equals negative 36, you could then probably just write down yes. Now, the alternative is that you actually go through and you just crank it out. You actually just come up with the solutions, and if they have an I in them, then they have imaginary solutions. And if they don't, well, then they don't have imaginary solutions. It's as easy as that. All right, let's take a look at the next free response problem. Number 26. The initial push of a child on a swing causes the swing to travel a total of 6 feet. Each successive swing travels 80% the distance of the previous swing. Determine the total distance to the nearest hundredth of a foot a child travels in the first 5 swings. Well, if they had said in 100 swings, I might do this a little bit different. All right. Also, the child would be on there for quite a while. But since they're just talking about 5 swings, I'm just going to write it out, right? On the first swing, I go 6 feet plus, right? So that's swing number 1. Now, swing number 2 is only going to go 80% of the distance of the previous swing. So that's going to be 6 times 0.8, right? That's going to be how far we go the next swing. And I don't want to know what that is right now. I'm not going to figure that out. I'm going to write out the entire sum and then just do it on my calculator. Now, the next swing is going to be this one times 0.08. So the next swing is going to be 6 times 0.8 squared. And now you probably see what's going on here. This is actually what's known as a geometric series, and there's a beautiful geometric series formula that you can use to find the answer to this, but I'm not going to do it that way. I'm going to show you just in a moment, right? First swing, second swing, third swing, right? We want to know the total distance the first 5 swings. We've got 3 of them. The next one's going to be 6 times 0.8 to the third, and the last one is going to be 6 times 0.8 to the fourth, right? That is what's going to give me the total distance, but I need it to the nearest hundredth of a foot. So here comes my calculator. Right, here we go. I'm going to have 6 plus 6 times 0.8 plus 6 times 0.8 squared plus 6 times 0.8 to the third plus 6 times 0.8 to the fourth. Right? That is going to be that entire geometric sequence. 6 plus 6 times 0.8 plus 6 times 0.8 squared, 6 times 0.8 cubed, not 6.8, 6 times. And I hit enter, I get 20.1696 to the nearest hundredth. That's going to be 20.17 feet. And this is as good of a time as any to discuss partial credit. You know, one thing that kills me about these tests is that if you write all of this out, you really know what's going on in this problem, right? But I could see a number of people doing this, right? You know, cranking it into their calculator or using the geometric series formula and then using your calculator and writing down this answer, 20.1696, right? And if you write down 20.1696, you know the math, you've written it down, it's great, and you're going to lose 1 out of 2 points because it says round to the nearest hundredth, which is a real shame. You know what I mean? To me, if I'm a teacher in class and this is a 2-point problem and you write this down, I'm going to give you like 1.75 points or 1.9 out of 2 points, you know what I mean? Because you've done everything beautifully. You just didn't read what you were supposed to round to. Unfortunately, on the Regents, we can't give a fraction of a point, so you would only get 1 out of 2 points if you wrote this particular answer down. So just keep that in mind. I know that you've heard that for years running, but it's good to hear it again. Let's take a look at problem 27. Solve algebraically for n. 2 over n squared plus 3 over n equals 4 over n squared. All right, let me make this a little bit bigger because I won't need all of this room to do this. Maybe I'll go up to 300. There we go. There's a lot of different ways to solve this problem. You know, for a lot of people, what they'll do is they'll multiply everything by n squared to clear out the denominators, and that is a perfectly good way to do it. Other people, though, will notice that that's an n squared, that's an n to the first, and that's an n squared. So one nice way of doing this problem is basically just getting a common denominator. In other words, a denominator of n squared. And I can do that by taking that second fraction, it's the only one I have to deal with, and multiplying the numerator and the denominator by n. Right? That's the way we always change a fraction to get a new denominator. I just took this and I multiplied n down here and n up there, and I got 3n over n squared. Why did I do that? Because now I can combine these two and write 2 plus 3n over n squared is equal to 4 over n squared. And the plain fact is, if you've got two fractions that are equal and their denominators are equal, then their numerators must be equal. So that now allows me to say 2 plus 3n is equal to 4. I can subtract a 2 from both sides. I'll get 3n is equal to 2. Divide both sides by 3. And n is equal to 2/3. It's as simple as that. All right. Now again, you'd also get n equals 2/3 if you multiplied both sides by n squared and had all of those cancel out. But get a common denominator works really, really nicely. All right, let me go back to fit width. Fit width. I don't know why, it's just fun to say. All right, let's take a look at 28. Factor completely over the set of integers. All right, factor completely. And this is a whopper. Man, I don't know how they exactly make this a 2-point problem, but hey, whatever, they did. So again, let me go in a little bit closer. Let's take a look at factoring this thing. Now, probably a lot of you will look at this and you'll go, oh, 4 terms, factor by grouping. And I like that. I like that. So I'm going to start by factoring by grouping. Now, others might look and say, but wait a second. There's an x to the fourth, an x to the third, an x squared, and an x to the first. Maybe I should factor an x out first. That's not bad either. That'll also work. We just have to factor until we can't factor anymore. And I did it both ways, and I decided I'm going to start with factoring by grouping. Okay? So I'm going to look at these first 2 terms, and I notice an x to the fourth and an x to the third. I can factor an x to the third out of both of these. So remember, factoring by grouping is the idea that I'm going to kind of look at the problem like that, and I'm going to rewrite this as x cubed times negative 2x plus 1. Now, if factoring by grouping is to work, then whatever I factor out of here, I really want to be left with a negative 2x plus 1. So it's very tempting to factor a 9x out of both of these, and that would be fine. The problem is if I factor a 9x out of both of these, I'll be left with 2x minus 1, literally the opposite of this. So what I'm going to do instead of factoring a positive 9x out of both of these is I'm going to factor a negative 9x out of both of them. And when I do that, right, what do I have to multiply negative 9x by to get positive 18x squared? That's going to be negative 2x. And of course, what do I have to multiply negative 9x by to get negative 9x? And that's going to be a positive 1. So now I see that classic factoring by grouping, and they both have a negative 2x plus 1 there. So I can now say that this is x cubed minus 9x times negative 2x plus 1. Hey, Red. There we go. Now, this one is as done as going to be because it's linear, right? Negative 2x plus 1, there's no GCF there, I'm done. Now I look at this. X cubed and 9x, there I'm going to pull that GCF of x out. All right? So I'm going to factor this one as x times x squared minus 9. And of course, I don't want to lose my negative 2x plus 1. So I have something like that. And now my final little piece is my x squared minus 9 is the difference of perfect squares. So it can be factored as x times x plus 3 times x minus 3, and then I have my negative 2x plus 1. And that is factored completely. Nothing else can be broken into a product after that. Now you will get the exact same answer if you factor an x out of this, all four terms right from the beginning. I just think it becomes kind of a parentheses nightmare when you do that. And you might be like, this is already a parentheses nightmare, Kirk, which I wouldn't disagree with. All right, I got to go back to this. There we go. Let's take a look at 29. The relative frequency table shows the proportion of a population who have a given eye color and the proportion of the same population who wear glasses. Given the data, are the events of having blue eyes and wearing glasses independent? Justify your answer. Now, let me just be very clear, right? Let's talk a little bit before we get into this table about things being independent, right? The idea here is very simple, right? Will having blue eyes change the probability that you wear glasses? Will having blue eyes change the probability you have glasses? Now, just for a moment, this can be kind of tricky for people because these are all sort of proportions. If you added all of these up, you'd get the number 1, meaning that this is everything, 100%. And I almost want you to think about it like this. Almost imagine that you have 100 people in a room. 100 people in a room. 14 of those people have blue eyes and wear glasses. 26 of those people have blue eyes and don't wear glasses. 11 of them have brown eyes and wear glasses, and 24 have brown eyes and don't wear glasses, etc., right? So the total number of people who wear glasses will be 14 plus 11 plus 10, or 36%, right? So if I total this, this is going, whoops, not 36, 35. I apologize, right? Now, the total number of people who have blue eyes, right, if I add these two together, right, that's going to be 0.4. So I can kind of think about this again in terms of like if there were 100 people in the room, 35 of them are wearing glasses and 40 of them have blue eyes. So what does it mean to be independent? Well, there's two ways that you can kind of take a look at this. One way is by saying, is the probability that a person has glasses, let me put GL for glasses, equal to the probability that a person has glasses given they have blue eyes? All right, I hate the fact that I have to use the GL and the BL, but we've got brown, green, glasses, you know what I mean? It's terrible. There's so many letters that are repeated here. So is the probability that they have glasses the same as the probability that they have glasses given that they have blue eyes? In other words, is the percentage of people who have glasses with blue eyes, any different than the percentage of, I said that wrong. Is the percentage of the blue-eyed people with glasses the same as just the percentage of all people with glasses? Well, the percentage of all people with glasses, as we just pointed out, is 0.35. So how do I figure out the percentage of the blue-eyed people that have glasses? Well, the percentage of people with glasses given they have blue eyes, right, is going to be, well, the number of people that have blue eyes and wear glasses, that's 14 people, or 0.014, divided by just the people who have blue eyes, which is 40 people, or 0.40. 0.40. Now, of course, I want to do that on my calculator. All right, so I'm just going to pull that out real quick. And might as well use the fraction bar, 0.14. Whoops, nope. Let's try that again. 0.14 divided 0.40, enter, and that's 0.35. Now, what does that say? Right? That says that whether you have blue eyes or just come from the population in general, right, you have a 35% chance of wearing glasses, which means that they're independent, meaning that like having blue eyes doesn't affect whether or not you have glasses, right? You're going to have a 35% chance of having glasses just if you come from the general population, and you're going to have a 35% chance of having glasses if you have blue eyes. So the answer is yes, they are independent. All right. Now, I do want to look at this just one other way, all right? There's something else that you may have learned, you should have learned, which was called the product test for independence. And this says, right, is the probability that I have glasses and blue eyes equal to the probability of having glasses times the probability of having blue eyes? Question mark. So if this is true, then the events are independent. If the probability of having both glasses and blue eyes is equal to the product of having the probability of glasses times the probability of having blue eyes, then they're independent. Well, the probability of having glasses and blue eyes is literally here, right? That's the probability of having glasses and blue eyes. So that's 0.14. Now, the probability of just having glasses, that's 0.35. And the probability of having blue eyes, that's 0.4. Right? And again, this is a test. Right? So I'm going to keep putting a question mark over there. And if this is true, then they're independent. And I'm not going to go into why this works or why it doesn't work. It's just what's called the product test for independent events. All right. Now, if I just do 0.35 times 0.4, I get 0.14. 0.14 equals 0.14. So yes, they are independent. All right. I personally like this one a lot better. Okay. And again, it's really simple. It's kind of like, you know, like any kind of test. When you see things like you're watching political coverage, I'm sure lots of you like stay up on election night, right, and watch political coverage, and they start to break things down. Like they say, well, candidate A is leading 52% to 48%. But let's break that into like the percentage of women that voted for candidate A and the percentage of men and the percentage of African Americans and Asian Americans and things like that. Because they're looking to see, right, if the proportion of, let's say, women voting for candidate A is the same as the overall proportion of people voting for candidate A. So if candidate A is getting 52% of the vote, but is getting 65% of the female vote, then being female and voting for candidate A are not independent of one another, right? Because you're more likely to vote for candidate A if you're a female in that situation, right? On the other hand, if 52% of the overall population is voting for candidate A and 52% of all women are voting for candidate A, then being a woman and voting for candidate A are independent events. All right, let's keep going. I just spent way too much time on independence. Problem number 30. For x not equal to 0 and y not equal to 0, the cubed root of 81 x to the 15th y to the 9th is equal to 3 to the a times x to the 5th times y to the 3rd. Determine the value of a. Well, I'm just going to say this. I hate the fact that they threw the x to the 15th and the y to the 9th in there, because they literally have absolutely nothing to do with this problem. I mean, just nothing. And here's why, right? When I take this thing, let's just for a moment, let's replace that cubed root with a 1/3 power, because that's what it is, and that'll also help us. Now, one of the many, many exponent properties is if you have a product like this raised to an exponent, then every one of the parts of the product can be raised to that exponent. So in other words, I have 81 to the 1/3, x to the 15th to the 1/3, y to the 9th to the 1/3, and then I'll just kind of keep writing this along, 3 to the a, x to the 5th, y to the 3rd. All right, and again, I just hate the fact that they have the x and the y in here, because you don't do anything with them. X to the 15th to the 1/3, well, 15 times 1/3 is 5. And 9 times 1/3 is 3. And they have to be that way. If they weren't, then where would those exponents come from, right? So really, the whole issue here is the fact that 81 to the 1/3 has to be, whoops, sorry, let me try that again. 81 to the 1/3 has got to be equal to 3 to the a. Now, how do I deal with that? Well, here's the deal, right? Start to think about powers of 3, right? So 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. And 3 to the fourth is 81, right? So 81 is the same as 3 to the fourth. So I can replace 81 with 3 to the fourth, right? I have to have it 3 to something because it's 3 to something over here. Now I'm going to use that exponent law that says if I've got something raised to an exponent raised to another exponent, I simply multiply the two exponents, and I'll get 3 to the 4/3 is equal to 3 to the a, and therefore a is equal to 4/3. All right, the x and the y are irrelevant on this, and therefore they're going to confuse quite a number of people, unfortunately, because it's really not the point at all. Oh, wow, okay. All right, let me just make sure. I accidentally skipped a problem on the geometry test. My apologies to those geometry students. I'm trying really hard not to do it again on this test. Can you believe that? We missed a problem. I cannot believe that. I forgot problem number 6 on the geometry exam, and it had to do with like the cosine and the sine of complementary angles. Anyway, whatever, totally different test now. Let's take a look at 31. Graph y equals 2 times the cosine of 1/2 x plus 5 on the interval 0 to 2 pi using the axes below. Okay, all right. Well, sometimes you have to graph a very, very simple trig function on the Algebra 2 exam. And this is a very simple trig function. Let's review some things we've already talked about. Okay, number 1, right, we've got a midline. We've got a midline of y equals 5. So one thing I like to do in a problem like this is go 1, 2, 3, 4, 5. And I like to just kind of draw almost a dashed line. All right. Now, we also have an amplitude equal to 2, which means that this curve is going to rise 2 units above 5 and go 2 units below 5, meaning that it'll have a maximum value of 7 and a minimum value equal to 3. All right? But what about that 1/2? How about the 0 to 2 pi, all of that kind of stuff? Well, the 1/2 is what's known as the frequency of the curve. And it literally tells you how many complete cycles this thing will do in 2 pi radians. We'll only get through a half of a cycle. Now, you've got your calculator. So there's no reason why not to see what the graph should look like, and then we'll get it down here and talk about what you have to do to make sure to get full credit. But first, let's actually just take a look at what it should look like on the calculator. All right, so I'm going to go and I'm just going to open up a new one of these things so I can get a fresh graph. I'm going to add a graph. I'm in radians already, so I'm good. So I've got 2 times the cosine of 1/2 x, where's my x? I think I would know that, not by now, plus 5. All right. Now, it's really critical for me to get the right window here. Okay, so I'm going to go into my menu, right? I'm going to go down to Window and Window Settings. Specifically, it says to go 0 to 2 pi. And there is absolutely no reason you can't do that. Now, what should my scale be? I could make it auto, but you know what I'd like it to do? I'd like, personally, for it to go by pi. Or I could maybe even make it go by pi over 2. I don't know. Now, y min, I'm going to make 0, and y max, I'm going to make 10, because that's my grid, basically. And there it is. So one way or another, right, I need a graph that looks like this. It's starting off at its maximum of 7, and it's ending after 2 pi at its minimum of 3. All right? And it hits its midline right there at pi. Okay? It hits its midline at pi. So how should I make that look over here, especially when it comes to this x-axis, right? Well, here's the key. You just have to decide, where do you want 2 pi to go? Do you want it to take up this entire thing? Do you want it to take up only 2 units? Do you want 2 pi to be there and pi to be there? You could do that. You just have to mark it. Now I'm going to take up my full advantage, right? I'm going to take those 10 units and I'm going to put 2 pi right there. All right, now that's really all I have to label, but I can't help myself. I'm going to go only 5 units over and I'm going to go to pi. Now, I could easily set up a table, but what I saw on the graph, right, was that I was at a maximum at 0, I'd hit my midline at pi, and then I was at my minimum at 2 pi. And so, there's my graph. All right, now you don't have to take up this entire thing. In fact, my first time doing it, trig graphs kind of come in quarters. So my initial thing was to have the 2 pi go only after 8 units and then pi after 4. And then I was like, it really doesn't make a difference. I mean, you could conceivably have something that looks like this with the 2 pi there and the pi here and kind of like, yeah, like that. And that actually would get you full credit. Full credit. Nothing says you have to take up the entire graph. All right. I like it though because I can like interpret the graph more. But you're not getting style points on the Algebra 2 exam. All right. If you did, I probably would have failed it. Okay, there we go. So there's my graph. And there's not much more to it than that. I kind of wish there was. Keep thinking, oh, maybe there's something a little more there. All right, let's take a look at 32. A cup of coffee, I could use one right now, is left out on a countertop to cool. The table below represents the temperature, F of T, in degrees Fahrenheit, of the coffee after it is left out for T minutes. Based on these data, write an exponential regression equation, F of T, to model the temperature of the coffee. Round all values to the nearest thousandth. All right, so regression, right? Specifically exponential regression. All right, now, how you do regression on a calculator, and you must do it on the calculator, is very calculator dependent. Very calculator dependent. Now, on the TI, all right, what I've done is I've actually already put this data into a spreadsheet. So there it is. I don't want to save my unsaved document. There is that data. All right. And what I like about the TI Inspire is you put the data in a spreadsheet format. And I have specifically labeled my X column time and my Y column temperature, and then I very carefully put the data in. Remember, this is a 2-point problem, and if you put even a single one of these incorrectly, you're going to get the wrong answer. And there's almost no chance then for partial credit, okay? So put the data in, carefully look through it, all right? And once you have all that data in, right, then at least on the TI Inspire, I'm going to go to Menu, I'm going to go to Statistics, I'm going to go to Statistical Calculations, and what I want is way down here, exponential regression, choice A, if you will. So I'm going to choose that. It asks me for an X list, so I go here, and for my X, I want my time. My Y list is the temperature of my coffee. Nothing else do I have to worry about. I hit OK, and here's my exponential equation. It has the form A times B raised to the X, where A is 169.136, etc. B is 0.9713, etc. And therefore, after all is said and done, and I get up to the correct page, I can now say that my exponential regression is either y equals 169.136 to the nearest thousandth, not hundredth, thousandth, 3 decimal places, times 0.971, and then I almost left one off. That is a completely okay way to write it. I know that they say f of t. You could do that as well. So you could also write it as f of t equals 169.136 times 0.971 to the t. Either one of those would be completely acceptable. All right, and that is really an issue of getting the calculator, getting the data into the calculator. If you're using something like the TI-83 or the 84 Plus, you know, you're going to put this data for t in L1, you're going to put this data for f of t in L2, and then you're going to do the exponential regression, L1 comma L2, and it's going to spit this out. And again, it's different if you have a Casio or a Hewlett-Packard or something like that. All right, great. I think we're about ready for another break and for part 3 questions. So let's take a little break, talk a little bit about our part 3 questions, and then we'll get on to them. All right, so we had 24 multiple choice questions worth 2 points apiece. We had 8 2-point questions, part 2 questions, worth 2 points apiece. All right, let me see if that works. Yeah, that's 32. And that gets us up to question 33, which is a part 3 question. Now, there are 4 part 3 questions, all right? And each one of them are worth 4 points apiece. Now, sometimes they can be broken up into kind of 2 part 2 questions. And this first one is sort of that way. So let's jump right into it and take a look at problem 33. On the set of axes below, graph y equals f of x and y equals g of x for the given functions. F of x equals x cubed minus 3x squared, and g of x equals 2x minus 5. All right, now we want to make an accurate of a sketch as we can, which means ultimately we are going to create xy tables. Maybe we only really need one for f of x. G of x, after all, is a line, all right? But let's make sure we know exactly what the graph should look like before we even generate the table of values. Now, please note, this particular grid is a 10 by 10 grid, all right? 10 by 10 grid. So let's go over to our calculator and let's see what our graph should ultimately look like. I'm going to do a new document, no, and I want a graph. All right, so I know we've got f and g, but here we have to do f1 All right, so there's my f1, and f2 is going to be 2x minus 5. All right, let me just really quickly try to get my arrow a little bit off of there. There we go. Now, all right, this is more or less the way my graph should look, but keep in mind that this is not a 10 by 10 by 10 sort of thing, right? This is negative 10 to 10 and then some weird negative 6.67 to 6.67. So just for a moment, I'm going to noodle with my window, and all I need to do is just get my y window to also be negative 10 to 10. So there's my negative 10 and my positive 10. So that is the way my graph should look. Okay, ultimately, that's the way my graph should look. Okay, but I need to graph it accurately on this grid. And especially when it comes to my cubic graph here, that's my graph in blue, there's not a lot of points I can plot, okay? So I need to get a graph that looks like that, and of course, you know, my linear graph, and I have to do it pretty accurately. So I'm going to get a table of values. I can do that on the TI Inspire by just hitting Control-T. That opens up a table, all right? I'm going to scroll up a little bit. My first column is that cubic, and what I notice right away is just crazy big values. You know, I'm never going to be able to plot negative 4 comma negative 112, negative 3 comma negative 54, negative 2 comma negative 20. In fact, the first thing I'm going to be able to plot is negative 1 comma negative 4, right? And then I've got 0, 0, 1 comma negative 2, 2 comma negative 4, 3 comma 0. Even the 4 comma 16 is not going to particularly work well for me, right? But let me just kind of collapse out of here. Right? Bring this up a little bit, and let me just create that table of values. It's always good to show your table of values, right? So I've got, even though I'm not going to be able to plot the negative 2, negative 20, I'm going to put it down there just so that we have it for reference. Negative 1 comma negative 4, 0 comma 0, 1 comma negative 2, 2 comma negative 4, 3 comma 0, and again, even though I won't be able to plot it, 4 comma 16. So I won't be able to plot that negative 2 comma negative 20, but negative 1 comma negative 4, right there, 0 comma 0, 1 comma negative 2, 2 comma negative 4, 3 comma 0, so there's another 0, and 4 comma 16. So I got something like way up here and way down there, so I'm going to get this curve that kind of looks like that, and I really do want to make it go through all the points. That's actually kind of a boo-boo, but there we go. All right, now, make sure to label. I don't have to write the whole equation, but make sure to have that f of x, right? And I really should make it go through this point as well. I just kind of missed it a little bit. Now, the 2x minus 5, that's a linear function. And there's a big part of me that does not want to write out a table for that. Of course, there's absolutely no reason why you can't write out a table. But keep in mind as well that for a linear function, I can easily graph the y-intercept at negative 5. 1, 2, 3, 4, 5. Right? And then I can use the slope of 2 to go up 2 and to the right 1, and up 2 and to the right 1, etc. So I'm going to end up having these points, and I don't have to do too many of them. I mean, it is a line. I'm then going to take my ruler, which I can't personally do on this, and I'm going to draw a straight line, hopefully much straighter than that, and I'm going to label it g of x. Okay, again, you don't have to say g of x equals 2x minus 5. You can, but you don't have to say that. All right? So there is my graph. And if this is a 4-point problem, okay, then I would say this is worth 3 out of the 4 points. But there's this last little extra, right? State the number of solutions to the equation f of x equals g of x. There was a problem really similar to this on the Algebra 1 exam, where they had to graph a linear function and an exponential function, and then they said state the number of solutions, explain. Right here, they just say state the number of solutions. So what you're always looking for is how many intersections. Right? And here, it's very simple. We've got 1, 2, 3. It's not necessarily at nice points, but there are 3. I'm not looking for the exact values. They're just looking for me to understand that when solving an equation graphically, I'm looking for the intersections of the 2 functions. That's it. All right. Let's go back to blue. Back to blue. All right, let's take a look at a Foucault pendulum. Number 34. A Foucault pendulum can be used to demonstrate that the Earth rotates. Awesome! And irrelevant. The time t in seconds that it takes for one swing or period of the pendulum can be modeled by the equation t equals 2 pi times the square root of L divided by g, where L is the length of the pendulum in meters and g is a constant 9.81 meters per second squared. The first Foucault pendulum was constructed in 1851, again totally irrelevant, this isn't a history exam, and has a pendulum length of 67 meters. That is a very, very long pendulum. 67 meters is 2/3 the length of a football field. I realize that isn't in the text and also irrelevant, but I find it cool and amazing. Can you imagine? Like, seriously, a pendulum that's like 2/3 the length of a football field. But I'm gonna believe him. I'm just gonna believe him. Anyway, determine to the nearest 1/10 of a second the time it takes this pendulum to complete one swing. Well, this really isn't math. This is more physics than math, and it's not even physics so much as just plugging numbers into a formula. So the formula says the amount of time it's going to take is going to be 2 pi times the square root of the length of the pendulum in meters, which is 67, divided by the acceleration due to gravity, which is 9.81. So it's just plug that into the calculator. That's just it. You know, there's nothing more, nothing less on it than that. And that is going to be, let's see, maybe I can just clear this up. No. And let's add a calculator. Okay, so here we go. We've got 2 times pi times the square root, might as well put the fraction in, why not? 67, oh, not 7, that's a shorter pendulum, although still pretty long. 67 divided by 9.81. All right, and enter, and it takes 16.4 seconds to the nearest tenth of a second. Now, I have to think, if this is a 4-point problem, which it is, that is worth 1 out of the 4 points, just 1. All right, maybe it's worth 2, but I think it's only worth 1. Because all you're being asked to do is take this formula and properly insert both the length of the pendulum, L, and the acceleration due to gravity, which is the 9.81. Now, let's look at the second part of the problem. Another Foucault pendulum at the United Nations building takes 9.6 seconds to complete one swing. Determine to the nearest tenth of a meter, the length of this pendulum. All right, well, finally, we've got a little algebra to do, right? Because in this case, right, we've got this equation, t equals 2 pi times the square root of L divided by G, right? And in this case, we know the time. It's 9.6. We certainly know 2 pi. We don't know what L is, but we know G is 9.81. All right, so in other words, what we're doing here is we're solving an equation involving a square root. But don't look at it that way. We're solving an equation for a variable that occurs only once. So yet again, we are simply going to use inverses. What has happened to L? We've divided L by 9.81. We've taken the square root of it, and then we've multiplied by 2 pi. So in order to solve for L, the first thing I'm going to do is divide both sides by 2 pi, and there is no way on earth that I'm going to take my calculator right now and figure out what this mess is. I'm not going to do it, right? Now, in order to get rid of the square root, what I'm going to do is I'm going to take the inverse of that, and I'm going to square both sides. And again, nope, not going to do it. Not going to even think about doing it. If you want to, more power to you, but I'm just going to leave this like that, okay? And finally, to solve for L, I'm simply going to multiply both sides by 9.81. Now again, don't get me wrong. If it helps you along the way to evaluate some of those intermediate steps, please, go right ahead. I don't mean to make you feel bad about having to do that. I just don't want to write down all the decimals. I mean, we're talking about an irrational number here in pi. So all of this is going to be ugly, ugly, ugly. And as soon as you start rounding early, you open up the possibility that you're going to introduce a rounding error. But now, all I have to do is go to my calculator, and I most certainly have to go to my calculator. And, whoops, not that yet. That's not what I want. And I'm going to put in parentheses, put in my fraction bar. I've got my 9.6 divided by 2 pi. All right, all of that squared times my 9.81 on the outside. And that is going to be 22.9 meters. It's the length of that particular Foucault pendulum. I get this very bad feeling that I'm mispronouncing Foucault. But, gotta move on. Yes, whether I'm mispronouncing it or not, I'll have to wait for that irate physics teacher to email me and go, how could you possibly mispronounce that name? All right, let's take a look at some statistics in problem number 35. In order to decrease the percentage of residents who drive to work, a large city launches a campaign to encourage people to use public transportation instead. Before starting the campaign, the city's Department of Transportation uses census data, census data, to estimate that 65% of its residents drive to work. The Department of Transportation conducts a simulation shown below run 400 times based on this estimate. Each dot represents the proportion of 200 randomly selected residents who drive to work. That's actually not correct. That's not what each dot represents. Each dot represents one of the simulations that they ran, and that simulation having a particular proportion. So again, understand like this whole idea. The whole idea is that they assume that the population, in the population that they care about, 65% of all the people drive to work. Then what they do is that they run a simulation. Now, how the simulations work is based on computers and random number generators and things like that, but they simulate pulling 200 people out of this population and seeing what proportion of those drove to work, right? And so if I look at a particular column, let me make this a little bit bigger. Let me go up to 200. Nope, no, that actually made it smaller, and then I went back a page. Oh, so many problems towards the end. There we go. Right? So if I look at a particular one of the columns, like the 0.65, and I don't know if that's really supposed to be that or that, but let's just go here, right? All of these dots represent like every dot represents a simulation where the proportion ended up being exactly that 65%. But you can see that just by chance alone, there were some proportions, right, that were in the 73% range driving to work, and there were some proportions way down here where barely over half of the people drove to work. Now, after they ran those 400 simulations, they then found the average of all the proportions, and that was 0.651. Notice how close that average is to the assumed proportion of the population, 0.65. But they also found the standard deviation of all these simulations, and that was 0.034. Okay? So now, after all of that, let's get into the actual question. All right, I got to make this a little bit smaller. There we go. Let's take a look. Use the simulation results to construct a plausible interval containing the middle 95% of the data. Round your answer to the nearest 100. Okay, 100th. Answers, I don't know. Okay, look, here's the plain fact. These questions come up a lot on this test. Whether you understand what's going on or not, and I imagine many of you probably don't, because this is some pretty high-level statistics that's kind of deep, okay? Even I feel a little bit shaky on these sometimes. But if you see an interval that represents the 95% of the data, then this is what you're going to do. You're going to forget about all these dots because they're totally irrelevant, and you're going to look at these two numbers, okay? And what you're going to do is you're going to take this standard deviation and you're going to add 2 of them to the mean, and you're going to subtract 2 of them from the mean. Because in a normal distribution, 90% of all the data falls within 2 standard deviations of the mean. So if you see middle 95%, and you're given a mean and a standard deviation, I want you to add 2 of these and subtract 2 of these away from the mean. So what you end up getting is you end up getting calculations that look like this. 0.651 minus 2 times 0.034, and that's going to be equal to 0.583, and 0.651 plus 2 times 0.034, and that's 0.719. Now, keep in mind, they want an interval that's to the nearest 100th, so we're going to say 0.58 to 0.72. Now, what does that even mean? What in the world does this interval even mean? Okay, what it means is that if truly 65% of the population drives to work in this, let's say, big city, New York City, LA, wherever, right? If I went and I grabbed 200 people, okay, I would expect the sample proportion to lie in between these two numbers by chance alone. Okay, if I got a good random sample, now most of them are going to be really close to 0.65, and you can see that in the interval, right? Most of these things lie very close to that 0.65, but 95% of them lie between 0.58 and 0.72. So just by chance alone, if 65% of the population drives to work, and I take a random sample out of this huge population of 200 people, then I would expect the sample proportion to be somewhere between 0.58 and 0.72 just by luck alone. Now, if I got anything outside of that, that would be very unusual, and it would tell me something strange might be going on. So let's take a look at the second part of this problem. 1 year after launching the campaign, the Department of Transportation conducts a survey of 200 randomly selected city residents and finds that 122 of them drive to work. Should the department conclude that the city's campaign was effective? Use statistical evidence from the simulation to explain your answer. Okay, well, let's take a look at what proportion of these 200 randomly selected residents drive to work, right? This is what's called a sample proportion. Oftentimes that's given the letter P, and if I do 122 divided by 200, I want to turn that into a decimal. So real quick, I'm just going to do 122 divided by 200, and that is 0.61. Now, you might say, well, I mean, originally, right, it was 65% that were going to be driving to work, but it looks like it must have been effective because now it's down to 61%. Except, here's the thing, that 0.61 lies in this interval. So this could have easily happened by chance alone and had absolutely nothing to do with their campaign to try to get people to drive less. In other words, the only way we could conclude that the campaign was effective is if we got a proportion that was lower than 0.58. If we got one that was higher than 0.72, we would conclude that not only was it not effective in making them drive less, it actually caused them to drive more. They were like, well, forget it. I'm getting in my car now. I used to take the bus, but considering that you want me to take the bus, I'm now going to drive. I don't know who would do that, but whatever. So the plain fact is, even though it seems a little bit counterintuitive, right, we should conclude that it was not effective because this value could have happened by chance sampling alone and not due to the campaign. So the answer is no, because this sample proportion fell into the 95% interval, so could have happened by chance alone. Now, don't get me wrong. It could have also happened because the campaign was effective. It could have actually happened because the campaign was effective, you know? Maybe not hugely effective, but maybe it did slightly lower the percentage of people that drive to work, all right? But we don't have conclusive statistical evidence of that fact because that falls in this interval. That can be a little confusing. All right, let's keep going. A system. 36. Solve the system of equations algebraically. I mean, you don't get very much more sort of algebraic than solving a system of equations. Now, this particular one, unlike that system of 3 equations and 3 unknowns in the multiple choice where we were like adding and eliminating and all of that, we're not going to do that here. We are going to solve this system by the age-old method of substitution. And specifically what we're going to do, and they always have to do this. Do you know what I mean? They couldn't just give us y equals here. They had to do y plus 5 equals 2x. They had to do that so that just momentarily we have to do the following. Right? We need to bring that 5 to the other side and make it a negative 5. And I tell you, if you put the 5 on the other side and keep it positive, you're going to be dead in the water on this problem. It is just not going to work out at all. But once you have that, y equals 2x minus 5, you can now take your 2x minus 5 and substitute it into this equation for y. And let's take it from there. So I'm going to have x squared plus 2x minus 5 squared is equal to 25. Now I've got to square out 2x minus 5. Some of you, I'm sure, can do that in your head. but others are going to want to FOIL it out, right? And we'll get 4x squared and minus 10x and another minus 10x and then a plus 25. So all of that is going to be 4x squared minus 20x plus 25. And that's just the 2x minus 5 squared, right? That's just this part of solving that equation. So I'm going to get x squared plus 4x squared, whoops, not minus 10, Kirk, minus 20x plus 25 equals 25. All right, let's combine a couple like terms, not much I can do there. 5x squared minus 20x plus 25 is equal to 25. And I'm really hopeful that at this point in your math career, when you're trying to solve an equation with an x squared in it, whether or not you're doing it by factoring or whether or not you're using the quadratic formula, you know you got to get it equal to 0. So right now this is equal to 25, which means I'm going to subtract a 25 from both sides. And I'm going to get 5x squared minus 20x. And hey, that's kind of weird. Those cancel, and I'm left with just equals 0. All right. Now, you could use the quadratic formula on this, but that would be weird. If you can factor to solve a quadratic, factor to solve a quadratic. In other words, I can actually factor a GCF out here, right? I can make this into 5x times x minus 4. All right, at this point now, I can use the zero product law, and I can say 5x is equal to 0, and x minus 4 is equal to 0. Here I can divide both sides by 5, and I'll get x is equal to 0. Here I can add 4 to a red 0, and I can get x equals 4. So those are my two x values that solve this system. To find my y value, right, I should either substitute it into this equation or this one, and this is my winner. I want to put it in here. There's no way I should put it in here to solve for my y. Look, y equals 2x minus 5. You don't get anything easier than that, all right? So, since y is equal to 2x minus 5, I can just do this. Y equals 0 minus 5, and y equals negative 5. And here, y is equal to 2 times 4 minus 5, y is equal to 8 minus 5, and y is equal to 3. All right, you can then write them as coordinate pairs if you like, and that's going to be 0, negative 5, and 4, 3. Or you don't have to. You could actually just sort of leave the work that I had before I even wrote all this down. You just have to make very clear what y goes with what x, all right? And again, if you've kind of organized your work nicely like this, that's no problem then. All right, I think we might have one question left. All right, so take one more little break, fit the width, and then we'll do the last question, which is surprisingly easy for a part 4 question. We're just moving along, folks. It is now 8:17 if you're watching this tonight with me. That's how you know it's live, by the way. Right, if it weren't really 8:17, if we really recorded this, let's say at 1 o'clock this afternoon when I wasn't exhausted, then how would I know it was 8:17? Unless I was like really sly about it and I like had like some kind of timer up on the wall and I was like somehow adding that to 6 o'clock. I don't know. You know, I suppose I could pull it off, but you know, like things like The Daily Show are always recorded like hours before they actually go on, and you always think to yourself, oh yes, they're live, but they're not. And they make fun of that every once in a while. I don't know why I even went off on that, except to say that we've got plenty of time to do this last question. So, part 4, right, it says answer the question in this part, right? A correct answer will receive 6 credits. And again, sometimes it's like a single question. And I hate it when that happens because, man, that's a big question. That tends not to be the case on the Algebra 2 exam. You can see it sometimes on the geometry exam, especially if there's some kind of big, beefy, like Euclidean geometry proof worth 6 points. Thankfully, that wasn't the case on the one we did last night. But this one is really kind of broken up for us, and I think it makes it a lot easier. So let's take a look at the last question on the Algebra 2 exam from last June, 37. The population in millions of people of the United States can be represented by the recursive formula below, where a sub 0 represents the population in 1910, and n represents the number of years since 1910. A sub 0 equals 92.2, and a sub n equals 1.015 times a sub n minus 1. All right, so before we even get into the first part of the problem, let's really kind of dig in and understand what this recursive definition tells us, right? First, it tells us that in 1910, right, the population of the United States was 92.2 million people. The second part tells us if we want to know the population in any given year after 1910, where n is the number of years, right, then we just take the population 1 year earlier and we multiply by 1.015. And that actually gives us the key to understanding the first question. Identify the percentage of the annual growth rate, or the annual rate of growth from the equation an equals 1.015 times a sub n minus 1. All right, I hope that this is easy, especially since Algebra 1, right? If we multiply each previous amount by 1.015, then our annual rate of growth is 1.5%. That's it, right? And they don't ask you to explain it. They don't ask you to talk about it. 1.5%, right? It's always 1 plus the rate, and if the rate is 0.015 and you're not sure, multiply by 100 and you're going to get your 1.5%. All right, easy enough. Let me go back to the width. All right, let's take a look at the second part of the problem. Write an exponential function p, where p of t represents the United States population in millions of people, and t is the number of years since 1910. Well, keep in mind, right, exponential models all kind of look like this. P of t equals a times b to the t, right? Where a is the initial amount, right? A is what you start with, and b is what you multiply by each year to get to the next year. Well, we were told that our initial amount is 92.2, and this is what we're going to multiply by each year. So it's really quite simple, right? P of t is 92.2 times 1.015 raised to the t. Now again, thinking about a 6-point problem, right? This is 1 point, and this is 2 additional points, so that's a total of 3 points so far, okay? Now, let's take a look at the last part of the problem, which should be worth the other 3 points. According to this model, determine algebraically the number of years it takes for the population of the United States to be approximately 300 million people. Round your answer to the nearest year. I love that, approximately 300 million people, you know what I mean? It's like, okay, yeah, I guess, you know what I mean? So could I go for 290? Could I go for 305 million? I don't know, you know what I mean? Anyway, the plain fact is what we need to now solve is the following equation. 92.2 times 1.015 to the t is equal to 300. And I want to round to the nearest year. Okay, so I am solving an exponential equation. And when I solve an exponential equation algebraically, right, and that's what it says, determine algebraically. I can't do it graphically, unfortunately. But when I do this algebraically and I solve an exponential equation, eventually logarithms are going to come into play. But before I do any kind of logarithm, the first thing I'm going to do is divide both sides of this equation by 92.2. Sounds like I'm talking about a radio station. Of course, young kids these days probably don't even know what those are. You know, it's kind of like Sirius XM, except with numbers. All right, so I'm going to get this at this point. All right, now again, I realize that it's probably very tempting to figure out what 300 divided by 92.2 is on your calculator, and you can totally do that. There's nothing wrong with that. okay? I'm going to leave it this way, though, for the time being. Now, I need to solve for this. Now, one thing you could do is take the logarithm base 10 of both sides, or the natural logarithm of both sides, or you could take the logarithm base 1/2 of both sides. It doesn't really matter. And you could then bring the exponent out. But what's cool is on all modern calculators, and trust me, you have a modern calculator, whether it's the TI-83 Plus, the 84 Plus, the Casio, the Hewlett-Packard, or the TI Inspire. And the easiest thing to do right now is to take the logarithm base 1.015 because it is the inverse of the exponential with the same base. So if I now do the log base 1.015 of both sides, and this is very kind of hard to write on this side, then these two cancel, and I'll literally get t equals log base 1.015 of 300 over 92.2. And that's pretty easy to do on my calculator, right? So all I need to do is go to my log. It will take any base whatsoever, log of base 1.015. And again, what I'm asking the calculator is something that for us is very difficult to think about, but for the calculator it's very easy. When you do a logarithm of any base, you are literally asking the calculator to tell you, what exponent do I need to raise this number to get this number? And I know that we don't know what 300 divided by 92.2 is. It's slightly north of 3 because 92.2 is close to 100. All right, so we're trying to figure out, well, what do I need to raise 1.015 to get a number that's a little bit bigger than 3? And I hit enter, and I have to raise it to the 79.24, etc., right? To the nearest year, that's equal to 79. Right? And that's it. 79 years. Roughly 1989, the year I graduated from high school. Little piece of demographic information there. Kind of cool. Yep, long time ago. Seems like forever. And that's it. That is the Algebra 2 exam. I didn't even have to turn to the formula sheet once. I was like going to the formula sheet constantly in the geometry exam. Volume formula for a cone, volume formula for a sphere, etc. I think I even went to the formula sheet once for the Algebra 1 exam. The Algebra 2 exam, I never went there. Don't get me wrong. There are some things on there that you could maybe possibly at some point maybe use, you know, especially like the geometric series formula. We could have used this formula on that one with the swing, right, in terms of like the total distance, but I didn't really need it, you know. But there's not much else on this particular formula sheet that really applies that much to the Algebra 2 exam. Don't get me wrong, there is the quadratic formula, and that could easily come up if you were solving for, let's say, the complex roots of a quadratic equation. And we certainly discussed it when we talked about the discriminant being negative and giving us imaginary solutions. But all in all, I didn't particularly need this formula sheet. Geometry students, all sorts of stuff over here they might want to use. People that are in, let's say, home ec, right? This would be great up here. Lots of great stuff in terms of like gallons and cups and pints and quarts and whatnot. This is still the biggest joke to me ever. The person who said, oh yeah, we really need people to know that 1 kilogram is 2.2 pounds, you know. And then they always give you these conversion factors anyway in the problems. Whatever. Not the point. Now I just want to get back to the beginning of the exam. There it is. All right. The Algebra 2 exam tends to be the hardest of the 3 Regents exams, and that makes all the sense in the world, right? It is your terminal Regents math exam. Now, those of you who really hate geometry proof might say, well, actually, I'm no big fan of the geometry exam, right? You know, maybe the Algebra 2 exam is easier for you. I don't know. Regardless, right, it took us about 2 hours and 20 minutes to work through that entire exam with me going through and explaining each question. Now, granted, I'd looked through the exam multiple times, so I definitely knew how to do all the problems, or at least I hope I knew how to do all the problems. I'm sure I'll probably get an email by somebody who's either complaining about how I mispronounced the Foucault pendulum or something else along those lines. I'm not sure. But regardless, right, we made it through the exam, and you will make it through the exam a couple days from now, all right? Take your time. Really use your calculator, right? There was a lot more graphing on this exam than either on the Algebra 1 exam or the geometry exam, especially if you've got trigonometric graphs that you have to either interpret or graph, like we had to on that graph grid. We also had that cubic graphed with the linear that we absolutely needed. And we also took a look at a logarithm graph, right, when we were thinking about like what was going on with that particular logarithm, all right? So your calculator can be extremely helpful on this particular exam if you know how to use it right. Don't forget to make sure to have it in radian mode, right, when you graph trigonometric phenomenon or whatever, all right? But all in all, right, you're going to do okay on this exam, all right? You're going to do great on this exam if you've really been there all year, paying attention and working hard, and you've studied for the past week. I know it's tough. The Algebra 2 exam comes on the last day of Regents testing, right? Your last class might have been a week and a half before you take this test, right? Which is why I hope you're watching tonight, and of course if you're not, then you're not even hearing this message. It's an irony. Maybe it's not an irony. Maybe it's a paradox. I don't know. Anyway, I'm not an English teacher. That much is certainly true. Anyway, I think I'm going to sign off now. I just want to wish all of you good luck. I want to wish all of you a great summer vacation. I hope that you rest and relax once you get done with that Algebra 2 exam. I hope you have nothing after it and you can just go home, kick back, relax, go to the pool, and enjoy yourself or whatever you happen to do during the summer. All right? I just want to say this has been the Algebra 2 live review by eMath Instruction. My name is Kirk Weiler. And until I see you again, keep thinking and keep solving problems.